Welcome to Chemistry, Buffer Solutions, and the Henderson-Hasselbalch equation. Break time during 0.5 Cess, Brox, data by Hertz are among the most important concepts in chemistry and biology. They resist changes in pH when small amounts of acid or base are added, making them essential for maintaining stable conditions in everything from laboratory experiments to the human bloodstream. B gave Henderson-Hasselbalch's equation. In this presentation, we will explore what buffers are, how they work using Le Chatelier's principle, the famous Henderson-Hasselbalch equation that lets us calculate buffer pH, different types of buffers, buffer capacity, common buffer systems, and their biological importance. Free time equals 0 to 3 Cess. Through 5 quiz questions and 5 fully worked problems, you will gain mastery of this essential topic.
In 1887, Swedish chemist Svante Arrhenius proposed the first modern definition of acids and bases. An Arrhenius acid is any substance that increases the concentration of hydrogen ions, H+, when dissolved in water. An Arrhenius base is any substance that increases the concentration of hydroxide ions, OH-, when dissolved in water. An acid-base reaction under this theory is simply H++ OH- yields H2O. Classic examples of Arrhenius acids include hydrochloric acid HCl, nitric acid HNO3, and sulfuric acid H2SO4. Classic Arrhenius bases include sodium hydroxide NaOH, potassium hydroxide KOH, and calcium hydroxide KOH. 2. The defining feature is the production of H+ or OH- in aqueous solution. In 1923, Johannes Bronsted and Thomas Lowry independently proposed a more general definition. A Bronsted-Lowry acid is a proton donor, a substance that gives up an H+ ion. A Bronsted-Lowry base is a proton acceptor. The beauty of this definition is that it makes the central role of proton transfer explicit. Every acid-base reaction is a proton transfer. Consider ammonia and water. NH3 accepts a proton from H2O, becoming NH4+. H2O donates a proton, becoming OH-. So ammonia is the Bronsted-Lowry base, and water is the Bronsted-Lowry acid. NH3 and NH4+ are a conjugate acid-base pair, differing by exactly one proton. Every Bronsted-Lowry acid has a conjugate base, and every Bronsted-Lowry base has a conjugate acid. The two differ by exactly one proton. When HA donates a proton, it becomes its conjugate base, A-. When B accepts a proton, it becomes its conjugate acid, BH+. The conjugate base of a strong acid is a weak base, and vice versa. A classic Bronsted-Lowry reaction is the dissolution of ammonia in water. NH3 accepts a proton from H2O, becoming NH4+. H2O donates a proton, becoming OH-. So ammonia is the Bronsted-Lowry base, and water is the Bronsted-Lowry acid. The reverse reaction shows NH4+ donating a proton back, becoming NH3. Another example. Acetic acid donates a proton to water, giving H3O+ and acetate. The species differ by exactly one proton. In the same year, 1923, Gilbert N. Lewis proposed the most general definition. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. In a Lewis acid-base reaction, the base donates a pair of electrons to form a new covalent bond with the acid. This definition is broader than Bronsted-Lowry because it includes reactions where no proton transfer occurs. and it works for reactions in any phase, gas, liquid, or solid. Classic Lewis acid-base reactions include the formation of the adduct between boron trifluoride, BF3, and ammonia, NH3. BF3 has an empty p orbital that accepts the lone pair of ammonia. Metal ions are Lewis acids. They accept electron pairs from water or ammonia to form complex ions. The silver-ammonia complex, Ag, NH3, 2+, forms when Ag+, a Lewis acid, accepts electron pairs from two NH3 molecules, Lewis bases. Even proton transfer reactions are Lewis acid-base at heart. Comparing the three theories. Arrhenius is the simplest, limited to aqueous solutions, defines acids as H+ producers and bases as O- producers. Bronsted-Lowry is broader, works in any solvent, focuses on proton transfer, gives us the concept of conjugate acid-base pairs. Lewis is the most general, based on electron pair donation, includes reactions without protons, and unifies acid-base chemistry with coordination chemistry. Each theory is a superset of the previous. Every Arrhenius acid is a Bronsted-Lowry acid, and every Bronsted-Lowry acid is a Lewis acid. Some substances are amphoteric, meaning they can act as either an acid or a base depending on the situation. Water is the classic example. It can donate a proton to a base, acting as an acid, or accept a proton from an acid, acting as a base. The autoionization of water, 2H2O giving H3O+ and OH- is a proton transfer between two water molecules. Amino acids are amphoteric, with both acidic carboxyl groups and basic amino groups. Aluminum hydroxide, AlO3, dissolves in both strong acids and strong bases, demonstrating amphoteric behavior. Bicarbonate, HCO3-, can act as an acid, giving carbonate, or as a base, giving carbonic acid.
Quiz question 1. According to Arrhenius theory, how does HCl behave when dissolved in water? Option A. It donates OH- ions, acting as a base. Option B. It donates H+ ions, acting as an acid. Option C. It accepts H+ ions, acting as a base. Option D. It does not dissociate in water. The correct answer is B. Arrhenius defined an acid as a substance that increases H+ concentration in water. HCl dissociates completely into H+ and Cl-, donating H+ to the solution. Quiz question 2. In the reaction NH3 plus H2O giving NH4 plus and OH-, which species is the Bronsted-Lowry base? Option A, NH3. Option B, H2O. Option C, NH4 plus. Option D, O-. The correct answer is A. NH3 is the Bronsted-Lowry base because it accepts a proton from H2O. H2O acts as the acid. The conjugate pairs are NH4 plus over NH3 and H2O over OH-. Quiz question 3. Which compound is a Lewis acid but not a Bronsted-Lowry acid? Option A, HCl. Option B, H2SO4. Option C, BF3. Option D, CH3COOH. The correct answer is C. BF3 is a Lewis acid because it accepts an electron pair into boron's empty 2p orbital, but it has no H plus to donate, so it is not a Bronsted-Lowry acid. Quiz question 4. What is the conjugate base of H2O in Bronsted-Lowry theory? Option A, O-. Option B, H3O+. Option C, O2-. Option D, H2. The correct answer is A. The conjugate base forms when an acid loses a proton. Water minus H plus gives OH minus. H3O plus is the conjugate acid of water, formed when water gains H plus. Quiz question 5. The autoionization constant of water, Kw, equals 1 times 10 to the minus 14 at 25 degrees Celsius. In pure water, what is the concentration of H3O plus? Option A, 1 times 10 to the minus 7 molar. Option B, 1 times 10 to the minus 14 molar. Option C, 1 times 10 to the 7 molar. Option D, 1 molar. The correct answer is A. In pure water, H3O plus concentration equals OH minus concentration because each ionization produces one of each. Kw equals H3O plus times OH minus equals H3O plus squared. So, H3O plus equals the square root of 1 times 10 to the minus 14, which is 1 times 10 to the minus 7 molar. This gives a neutral pH of 7. Problem 1. Identifying conjugate acid-base pairs. For each reaction, identify the Bronsted-Lowry acid, base, conjugate acid, and conjugate base. First, HNO2 plus H2O giving NO2 minus plus H3O plus. HNO2 donates H plus to H2O, so HNO2 is the acid. H2O accepts H plus, so water is the base. After losing H+, HNO2 becomes NO2-, the conjugate base. After gaining H+, H2O becomes H3O+, the conjugate acid. Second, CH3NH2 plus H2O giving CH3NH, 3+, and OH-. CH3NH2 accepts H+ from H2O, so CH3NH2 is the base, H2O is the acid. The answer summarizes both pairs. Problem 2. Ranking acid strength from conjugate base stability. Rank HClO, HClO2, HClO3, HClO4 in order of increasing acid strength. Step 1. Acid strength depends on conjugate base stability after H+ loss. Step 2. HClO dissociates into H+ and ClO-, charge localized on one oxygen. Step 3. HClO2-, resonance delocalizes over two oxygens. Step 4. HClO3 gives ClO3-, resonance delocalizes over three oxygens. Step 5. HClO4 gives ClO4-, resonance over 4 oxygens, most stable. Ca about 10 to the 10. Order: HClO less than HClO2 less than HClO3 less than HClO4. Problem 3. Lewis acid-base adduct formation. Predict the product and identify the Lewis acid and base in the reaction between AlCl3 and Cl-. Step 1. Al in AlCl3 has 6 valence electrons. It is electron deficient with an empty 3p orbital. Step 2. AlCl3 is a Lewis acid. It can accept an electron pair. Step 3. Cl- has 4 lone pairs. It is a Lewis base, donating 1 lone pair to Al. Step 4. Product AlCl4-. Aluminum has 8 electrons, tetrahedral geometry. Step 5. Hybridization changes sp2 to sp3, trigonal planar to tetrahedral. Problem 4. Amphoteric behavior of AlOH3. Write equations for its reaction with HCl and with NaOH, and classify according to all 3 theories. Step 1. As a base, AOH3 plus 3H plus from HCl gives Al3 plus plus 3H2O. AOH3 accepts H plus. Step 2. Arrhenius. AOH3 reacts with H plus as a base, consuming OH minus. Step 3. Bronsted-Lowry. AlOH3 accepts H plus as a base. Step 4. As an acid, AlOH3 plus OH minus gives AlOH4 minus. It donates H plus. Step 5. Lewis. Al3 plus is Lewis acid, O minus is Lewis base. Answer: AlOH3 plus 3 HCl gives AlCl3 plus 3 H2O. AlOH3 plus OH minus gives AlOH4 minus. Problem 5. Calculating pH of a weak acid. Calculate pH and percent ionization of 0.100 molar acetic acid with Ka equals 1.8 times 10 to the minus 5. Step 1. Ice table initial. CH3 COOH equals 0.100 molar, H plus equals 0, CH3 COO minus equals 0. Step 2. Change minus X plus X plus X. Equilibrium 0.100 minus X, XX. Step 3. Ca equals X squared over 0.100 minus X equals 1.8 times 10 to the minus 5. Assume X much less than 0.100. Step 4. X squared equals 1.8 times 10 to the minus 6. X equals 1.34 times 10 to the minus 3 molar equals H plus concentration. Step 5. pH equals negative log of 1.34 times 10 to the minus 3 equals 2.87. Percent ionization equals X over 0.100 times 100 equals 1.34%. Let us bring everything together in a comprehensive review. Acid-base titration curves are graphical representations of pH change during neutralization. 5 key concepts form the foundation. First, the equivalence point is where moles of acid equal moles of base, and its pH depends on the strength of the acid and base involved. Second, the half equivalence point reveals the pKa of a weak acid, because at that point, HA and A- concentrations are equal. Third, the buffer region before equivalence resists pH change and follows the Henderson-Hasselbalch equation. Fourth, polyprotic acids display multiple equivalence points, one for each proton. Fifth, indicator selection must match the pH jump of the titration. The key formulas to remember are MAV, A equals MBVB for monoprotic titrations, pH equals pKa at half equivalence, and the Henderson-Hasselbalch equation. Thank you for learning with us.